Hi, this is lesson number 20, originally posted on May 20th. And today we're going to talk about acids and bases. We're going to do some calculations. This is the first of two that we'll be all looking at these calculations. All right, so a reminder that there's SI and Zoom. This week, the week of May 20th, we have office hours. Homework is due on Wednesday and Friday. Next week, May 25th through 29th, there will be no lesson or office hours on May 25th, but there'll be lessons on Wednesday and Friday. Okay, those lessons will not be on test 3. So test 3 will be lesson 13 through 21. So next lesson is the last one for test 3. A reminder that there's a quiz number 3 on May 27th and a review on May 29th. The homework for this one is a combination of number 19 and 20, and it'll be on sapling due Wednesday, May 27th at midnight. All right, so let's talk about a review. Last time we talked about strong versus weak acids, and we said that Ka is a way to indicate it. Remember, strong acids dissociate fully, weak acids only partially. And remember that Ka is going to be the amount of H plus over the acid itself. So the bigger Ka is, the stronger it is. So if I look at these three acids, okay, they're all weak because they're all fairly small Kas, but HF, that's the biggest Ka, so that's the strongest. Then, looking at them, H2PO4 minus, that's the second biggest Ka, and then finally HClO. All right, what are the conjugate bases of these acids? Well, conjugate bases are what happens, or what's left over after we lose an H+, because that's what acids do. So, if I have HCl and it loses an H+, it'll become ClO minus. If I have H2PO4, it'll lose one of these and it'll become 2 minus. And then HF will become F minus. Okay? So I just go ahead and take away an H+. And now 3 asks, which of these acids will have the strongest conjugate base? Well, strong acids produce weak bases, right? So if HClO is the weakest of all the acids, it's going to form the strongest conjugate base, okay? HF is going to form the weakest conjugate base. F minus will be the weakest base. All right, so that's a review of last time. Now we're going to go ahead and we're just going to look at the ionization of acids and bases, right? What happens when I have an acid, I put it in water, and it produces H+. Or when I have a base and I put it in water and it accepts an H+. And we're going to do calculations for first pH of a strong acid, then pH of a strong base, pH of a weak acid, and then you guessed it, pH of a weak base. These first 3 we'll do in this lesson. Number 4 we'll do next lesson. All right, now there is one thing, we'll go over this. We're always going to assume that water ionization is negligible. What that means is that any H plus or OH minus that forms is due solely to the acid or base. All right, so let's start by looking at what happens in pure water. All right, in pure water, I have H2O. My H2O, some of that is going to dissociate to form H plus and OH minus. But they're going to be equal amounts. And so I can go ahead and I can say the pH here is going to be 7. Right? That means it's neutral. Let's say instead we have a strong acid and we put it into that water. So I'm going to put HCl in there. HCl is going to completely dissociate. What that means is that my HCl is going to go and it's going to form H plus and Cl minus. So you can see once I put it in the water, I no longer have HCl. All I have is H plus and Cl minus. By the way, I've removed the H2O, right? There's still water there, obviously, but I'm just thinking about the things that form ions. So now if I look at this, I have a lot more H plus than I have OH minus. And so my pH is going to be less than 7. All right, so let's look at this in detail. Let's look at the calculations. All right, so let's say we want to know the pH of 0.04 molar HCl. Now, HCl is a strong acid. It's one of those that we are told that we should know is a strong acid, right? Hydrochloric acid. And so HCl, when I put it in water, it's strong, so it's going to form H plus and Cl minus completely. So it goes all the way to the right. I don't even write that reverse arrow. And so what this means is if I start off with 0.04 molar HCl in water, it's going to go ahead and it's going to form 0.04 molar H plus and 0.04 molar Cl minus. I don't really care about the Cl minus. I care about that H plus though, because that's 0.04 molar. I can say that pH equals negative log of that H plus. Okay? And when I do this, I'm going to get 1.4 for my pH. So all I do is I take my HCl, I turn it into H plus because it's strong, and I can calculate my pH from that. Okay? All right, here it is on the screen. Okay? Notice that it makes sense. I'm told I put an acid into water. So it makes sense that I will have a low pH, because that's what acidic means. All right, now I just want to go through one example here at the bottom. Let's say instead of 0.04 molar HCl, let's say I put in a very tiny, small amount of HCl, 4 times 10 to the minus 12 molar. That would form 4 times 10 to the minus 12 molar H plus. And if I were to look at that, that would mean that pH equals negative log of this 4 times 10 to the negative 12. And what I get is a pH of 11.4. But that doesn't make sense because I put acid into water, so it should be acidic. And that's because the H plus that forms from this is so small in comparison to the H plus from water itself. Okay? So this only works if we assume that the water ionization is small in comparison to other things, right? And that's what we're always going to do. All right, so that is pH of a strong acid. I just figure out my acid concentration, that equals H plus, and I plug that in to get pH. Now let's move on and let's talk about a strong base. So when I put a strong base in water, such as NaOH, it completely dissociates. So what's going to happen is this NaOH is going to form Na plus and OH minus. You can see that over here on the right where I have a bunch of Na plus and a bunch of OH minus. I don't care about the Na plus. But notice I have a lot more OH minus than I have H plus. So that means it's going to be basic. My pH is going to be greater than 7. All right, so let's go ahead and let's do that same problem we did earlier, except now we're going to look at a base. So we have 0.04 molar NaOH, and we want to know what its pH is. All right, so if I have NaOH, it's going to form Na plus and OH minus. Okay? It's strong. That's what strong bases do. They completely dissociate. All right, so if I have pH of 0.04 molar NaOH, that's going to give me 0.04 molar OH minus. And now, I have this 0.04 molar OH minus, so I might think, oh, let's plug that into pH. Well, remember, pH equals negative log of H plus. This is an H plus. I need to find H plus. And this is where we have to remember what we did 2 times ago, which is Kw equals H plus times OH minus. So my H plus concentration equals Kw over OH minus. That's 1 times 10 to the minus 14 over 0.04. That's going to get me a really small number. If it doesn't get me a small number, go back, make sure you understand how that calculator works when we're doing these calculations. So this is my concentration of my H plus. So now I can plug that in. So pH equals negative log of 2.5 times 10 to the minus 13. Okay, log of this, that's going to get me 12.6 for my pH. Does this make sense? Yes, because I put a base in there, so I better get something that's going to be basic. All right, so here it is on the screen. My 0.04 molar NaOH produces 0.04 molar OH minus. I do the calculation to find H plus, plug that in to find my pH. All right, now there is one thing in the same way that the OH minus from this base has to be greater than the OH minus from water ionization. If I just put in a tiny bit of OH minus or NaOH, I wouldn't be accounting for. So just remember that, hey, we need to make sure we're putting in enough that we have more than the water ionization. Okay, so let's have you guys do a problem. This is video problem 20A. You're going to figure out the pH of a 0.2 molar NaOH solution. All right, so do that, come back, and then we'll look at it. Okay, so that was pH of a strong acid and a strong base. So far, fairly easy. The reason being is they fully dissociate. When I've been writing them on the board, I put an arrow, one-way arrow. I don't do the equilibrium. But let's say we have a weak acid. If I have a weak acid, it becomes more difficult. Okay? So let's say I want to find pH of a weak acid. Now I have to use an ice chart or an ice table. Okay, let's understand first what happens, right? So let's say I have some water, which has H plus and OH minus, and all of a sudden I put in some HF. What's going to happen? Well, that HF is going to only partially dissociate. So I'm going to get some H plus and F minus, but I'm also going to have some HFs left over, right? So I'm not going to be able to, like I did for the strong acid, say, hey, all of it dissociates. Instead, I need to figure this out. Okay, so let's go ahead and do this problem. We're going to find the pH of a weak acid, right? And we want to do it, so we're going to find the pH of a 0.534 molar solution of formic acid. That's HCO2H. Yeah, so we know its initial concentration. We're given its Ka, and we want to figure out what its pH is. All right, so the first thing we have to do is if we're told something's a weak acid, we need to write down its equation. Right? So it's HCO2H going to form H plus CO2H minus. Okay? I took away this one. You could take away the other one. It doesn't matter. Actually, on the board, I took away that one. So let's just do it for completeness. It doesn't matter. All right. My Ka for this is 1.8 times 10 to the minus 4. Okay? What does that mean? That means that overall, I'm only going to get a tiny bit of this producing H+. Most of it is going to stay as my formic acid. All right, so we're going to do an ice table. This is why I told you you're not going to be able to run away from them, unfortunately. All right, so what are we given? We're given that I have 0.534 molar of my acid. And I'm not told anything about HCO2 minus, so we have none of that. And then I do actually start off with some H plus. I start off with 1 times 10 to the minus 7. But that number is small enough that we're going to assume it's 0. Okay? It just makes life easier. All right? And this is what I've been talking about. We have to assume that water ionization is negligible. Right? We have to assume that this doesn't matter. Okay? All right, so what's my Q? My Q is going to be H plus times HCO2 minus over HCO2H or 0. If I have something where I have no products, that means Q is equal to 0. All right, so Q is equal to 0. K is equal to 1.8 times 10 to the minus 4. So it's going to shift towards the right. Okay? So that means these are going to be positive, positive, negative. I have 1, 1, 1, so this will be minus x, plus x, plus x. Okay? That means this will be 0.534 minus x. This will be x. This will be x. Okay? Because it's 0 plus x. That's just x. All right. Now, I go ahead. I start off with my initial, found Q, found the shift, found the changes, found the equilibrium in terms of x, and now I plug it back in. So I have K equals x times x, so x squared, over 0.534 minus x. And this is going to be equal to 1.8 times 10 to the minus 4. All right, now can I assume that x is small? Well, I can assume that x is small if both Q and K are small. They're both smaller than 0.01. So x is small. Okay, so what that means is I'm going to assume that this is just this. Okay. Remember, if I make an assumption, I should come back later and check it. So I assume that 0.534 minus x equals 0, equals 0.534. Okay. Now I can rearrange this. So x squared equals 1.8 times 10 to the minus 4 times bracket 0.534. Okay. We're going to just do that right here. Okay. So that means x squared equals 9.612 times 10 to the minus 5, and x is the square root of this, and that's going to be 9.8 times 10 to the minus 3. Okay, so that is my value for x. Okay, now I can go ahead and use this to figure out all my equilibrium concentrations. All right, so this is going to be 0.534 minus this. That's going to get me 0.524. This is just going to be 9.8 times 10 to the minus 3. And this is going to be 9.8 times 10 to the minus 3. Okay? All right. Once I have these, I can do two things. I can check my work. Right? So x or k will be 9.8 times 10 to the minus 3 squared over 0.524. That's going to get me 1.83 times 10 to the minus 4. Notice that's very close, so I can check off. Let's go ahead and check our assumption. We assumed that it was 0.52 or 0.534. It's actually 0.524. We always put it over the actual value. And this looks like it's going to be fairly small. It's going to be 1.9%. So that passes the 5% rule. All right, but let's remember, what are we actually asking for? We're asking for the pH of this, right? So if we're asking for the pH of this, I don't care about HCO2H. I don't care about HCO2 minus. I care about my H plus. So if I want to find pH of this, I just do negative log of this value and I get 2.0. That is my pH. Does it make sense? Well, I added in an acid and I get a acidic pH. So it makes sense. All right, let's look at this on the paper or on the screen. So first thing we do is we do an ice table. We figure out which direction it shifts. Then we plug it into our value for K. And then we solve. Okay? Now there's one last thing we should talk about this, and that's actually at the bottom of this screen, but we'll do it on the paper or on the board, and that is the percent ionization. Okay? So percent ionization is always the amount of H plus at equilibrium, right here, over the amount of acid, in this case HCO2H, we had initially times 100%. Okay. All right, so I'm going to use this equilibrium value, 9.8 times 10 to the minus 3, over 0.534 times 100%, and that's going to be 1.8%. That's my percent ionization. What does 1.8% mean? That means of my HCO2H, only 1.8% of that got turned into H+. This is a weak acid. If this was a strong acid, this number would be 100%. And that's why the calculations are a lot easier, right? This is a weak acid. Okay, so you are going to do another problem. This is video problem 20B. Right? So we're going to look for a solution with an original concentration of 2 molar HF. Okay, we're going to need to use an ice table. And so the first thing you need to do for an ice table is you need a reaction. Okay, so remember, HF is a weak acid. So start off by figuring out the reaction involved with HF being an acid. All right, so that is it for this lesson. We went through strong acid, we went through strong base, and now we've just gone through weak acid. Next time we'll move on to weak base, and then we're going to talk a little bit about something called polyprotic acids. All right, so that's lesson 20. Remember, sapling homework for this will be due Wednesday, May 27th, and all of this is building up to our test number 3, which will be on June 1st. And this is on lessons 13 through 21. All right, bye-bye.